So welcome to the tutorial on phase diagram. Here we are going to discuss some of the numericals related to the concepts of phase diagram. The first problem that we are going to discuss on binary isomorphous alloy. As we know that copper nickel system is a binary isomorphous system. Okay. So here the problem is determine the composition of each phase in a copper 40% nickel alloy at 1250 degrees centigrade. Okay, so it's a copper nickel alloy where the composition of nickel is 40% and the temperature is given 1250. So first thing you have to find out what are the different phases present and their composition. So first part you have to find out the composition of the phases. The second part you have to find out the amounts of the alpha phase or the solid phase and the liquid phase at 1250 degrees centigrade of the same alloy composition. Okay, so you have to find out the mass fraction in the second part. In the first part you have to find out their compositions. Okay, so for that what we need the phase diagram of the copper nickel system. So here you can see the copper nickel system. It's a isomorphous system. They have extensive solid solubility as well as definitely liquid solubility is also there. So the phase diagram is like this. This is the liquidous line, this is the solidus line, like that. So the temperature is 1250 degrees centigrade. So the first step is that at 1250 degrees centigrade, so 1250 degrees centigrade, and what is the composition? 40% nickel. So 40% nickel and 1250 degrees centigrade, so it is something here in this region. So this is the point indicating that. So to find out the composition, what we have to do? First thing is we have to do the tie line, because with the help of this tie line we can find out the composition. So we draw the tie line. What is tie line? Tie line is basically an isothermal line that is drawn at that temperature in the two-phase region, and definitely it will cut the liquidous line at a point and the solidus line at a point, and corresponding to those points the compositions you can see corresponding to this point where this tie line cut the liquidous line is 32 and the composition corresponding to this point is 45. So where the tie line cut the liquidous and solidus line will give you the composition of the liquid phase and the solid phase. Okay, so here is the liquid region. So this is the liquidous line, so it cut the liquidous line at this point. So what is the composition? That is 32. So 32 is the composition of the liquid present. So basically if you see the microstructure of this point where it is 40% nickel and the temperature is 1250 degrees centigrade. So there if you see the microstructure, there is some portion which is solid. Say these are alpha, and the remaining portion is liquid. Now in this liquid, what are the components present? The component presents are nickel and copper. In the alpha solid phase, what are the components present? Components are again copper and nickel, but their compositions are different. That means what is the fraction of nickel present in the liquid portion? That is what is the question that you have to find out, the composition of each phase. That means you have to find out in the liquid what fraction of nickel and what fraction of copper. In alpha phase, what fraction of nickel and what fraction of copper is there. So this is what we mean by the composition of each phase. So the answer is very straightforward. We can find out where if this tie line will cut this liquidous line will give you the composition of the liquid. So composition of the liquid, if C represents composition, L represents liquid, so composition of liquid is what? That is 32% nickel. So this is what is the composition. So what is the composition of the solid alpha phase? In the alpha phase composition is 45 because the tie line cut the solidus line at this point. So 45% nickel is the composition of the solid that is present. But the overall composition, remember, the overall composition of the system is 40%, but the liquid having 32% and solid alpha having 45% nickel composition. Okay, so in the next part we'll have to find out that what fraction of solid is there and what fraction of liquid is there. Okay, so mass fraction that you have to find out. So the second part, we have to find out, calculate the amount of alpha, and if you can find out the amount of alpha definitely in percentage, then 100 minus that will be the amount of liquid. So your problem is to find out what fraction of solid is there, what fraction of solid is there. Suppose this is the solid portion and the remaining portion is liquid. This is liquid portion and this is, so you have to find out this fraction. So how can we do that? So to find out the mass fraction, remember we have to use the lever rule. We have to use the lever rule. Lever rule is used to find out the mass fraction or the weight fraction. So you have to find out the weight fraction of the solid phase alpha. So weight fraction of solid phase alpha is equal to what? Is equal to, if you consider this is what is the overall composition, where it cuts the liquid as line, where it cuts the solid as line, corresponding composition we have already got. Now if you write this length as R and if you write this length as S, then to find out the solid composition fraction, solid fraction, the solid is in this area, so we have to take the opposite term first. So it will be R divided by the total length, that is R plus S. Okay, so to find out the alpha or the solid composition, what we have to take? Solid is in the right side, we have to take the opposite one, that means R in the numerator. Okay, and in the denominator it will be R plus S. So what is this R? R is basically this length. What is this length? So this composition minus this composition. What is this composition? 40. What is this composition? 32. So R is what? 40 minus 32. And what is R plus S? R plus S is the total length. So what is that? This composition minus this composition. This composition is 45, this composition is 32. So it will be 45 minus 32. Clear? So this will be the weight fraction of alpha. So if you can find out the weight fraction of alpha, then definitely 1 minus that will be the weight fraction of the liquid. Okay, so if you do this calculation, you can find out the result. So this is what is W alpha, that means 62% is basically solid and the remaining portion, that means 38%, is liquid. Clear? Now coming to the next problem. So this problem is on binary system, but now it is not isomorphous, it having limited solubility, but it's a eutectoid alloy. Okay, not eutectoid, actually lead tin system is not eutectoid, it is eutectic. Okay, I'm sorry, eutectic. Okay, so this is a eutectic system. Lead tin is eutectic system. So anyway, the problem is for a 40% tin and 60% lead. So the composition, overall composition of the alloy is given. The temperature is also given, 150 degrees centigrade, 150 degrees centigrade. And the question is, what phases are present? This is the first part of the question. What phases are present? And the second part, what are the compositions of the phases? Exactly similar kind of questions. And then the second part, you have to find out their relative amounts of the phases present. That means the mass fraction that you have to find out. Okay, so for that, what you need, you first need the phase diagram. So from the phase diagram we have to solve this one. Okay, so first take the first part of the problem. So first part of the problem, it is the overall composition. In the x-axis you see this is the composition of the weight percent of tin. So what is the weight percent of tin here? It is 40% tin. So this is what is the overall composition. So this is 40%. So corresponding to this, what is the temperature given? 150. So this is 150. So the point you can easily identify that this is the position indicated by this composition and temperature. So question is, at this position what are the phases present? Definitely you can see it is a two-phase mixture region. That means alpha phase and beta phase are in a mixed condition here in this region. So two-phase mixture. So two phases are present. What are the two phases? One is alpha, another one is beta. What is alpha? Alpha is basically a lead rich phase and beta is a tin rich phase. Okay, alpha and beta. Second part is of what phases are present. The second part, what are the compositions of those phases? So you have to find out the composition. And how can we find out the composition? To find composition, we have to draw the tie line. So this is what is the tie line. Through that point we have to draw an isothermal line, and we'll see where these isothermal lines cut in this two solvers line. Okay, so from this, if you see, this is what is the composition, and here you can see this is what is the composition. That means in the alpha some tin is there, some lead is there. In beta also some tin is there, some lead is there. So what is the composition of that alpha? So in alpha the composition is this C alpha, this composition. Okay, so here from this diagram you can see this composition is 10. So composition of alpha, you can see what, that is 10%. And what is the composition of the beta? That you get from here, and that is 98%. You see beta is 98%. Remember, these are the composition of weight percent of tin at the percent tin. Okay, so we can find out the composition of each phases. This is the first part. Second part of the problem is you have to find out, okay, we have understood that alpha and beta phases are there, but the question is what fraction of alpha is there, what mass fraction of alpha is there, what mass fraction of beta is there. So how can we find out the mass fraction? We have to use the lever rule, right? So if you use the lever rule, what will be that? You just write this is R, you write this is S. So what is the mass fraction of alpha, tell me? So alpha is in this side, so which side you have to take to find out alpha? That is S. So S will be in the numerator and the total length will be in the denominator, that is R plus S. So now tell me, what is S? So S will be this composition minus this composition. What is this composition? 98. What is this composition? That is 40. So 98 minus 40, that is S. And what is R plus S? R plus S is the total length. That means this composition minus this composition. So this composition is 98 and this composition is 10. So 98 minus 10. Okay, if you do the calculation, you will get the mass fraction of alpha phase present. What will be the mass fraction of beta phase present? Simply 1 minus W alpha. Okay, remaining portion. Or you can also find out in a way that W beta will be, since you want to find out the beta fraction, so you have to take the opposite term, that means R by R plus S. You can also do in that way also. Okay, so this is how we can do the problem. So you can find out W alpha and W beta. Okay, and you can see you can find out W beta simply by 1 minus this in that way also. Okay, now coming to the next problem, where this problem is from iron carbide phase diagram. Okay, now in this case the problem is there is a composition of iron carbon where carbon percentage is 0.35% and 99.65% is iron. Okay, so 0.35% is the composition of carbon in that alloy at a temperature just below the eutectoid temperature. Determine the following things. Okay, what you have to find out? You have to find out the fraction of the total ferrite and cementite phases present, to find out the fraction of pro-eutectoid ferrite and pearlite, and the fraction of eutectoid ferrite. Okay, so first we need the phase diagram. So this is not the whole iron carbide phase diagram. This is only the portion where the eutectoid reaction is taking place. If you remember, corresponding to 0.76 weight percent. So what is this composition? 0.76 eutectoid composition, and the temperature is 727. Okay, so here the eutectoid reaction takes place where austenite, here is it is austenite, is transformed into pearlite. Pearlite is what? Pearlite is basically ferrite, alpha ferrite, and cementite on the other hand. Okay, so here in this region it is basically ferrite alpha. Okay, in this region, in this small region, this is basically ferrite. Now this problem is not exactly the eutectoid composition, but the composition is 0.35% carbon. 0.35% carbon means maybe at this region. Okay, say this is the 0.35% carbon. So at 0.35% carbon, and the temperature has been told just below the eutectoid temperature. If you consider this is the eutectoid temperature, consider just below the eutectoid temperature. Let us consider this is F point, which is just below the eutectoid temperature. Okay, so what kind of transformation takes place? If you come down from a very high temperature, gradually if you cool it, you will find that here it is austenite, the whole thing is austenite, which is a solid phase, and gradually if you go down, you will find this is a region of a two-phase region where ferrite and austenite is there. So two-phase region, ferrite and austenite in this region. Here you can see within austenite gradually the ferrite phases are forming. Okay, and here you can see just above the eutectoid temperature at the point E, you see ferrite phases has been formed. A large amount of ferrite phases has been formed, and the remaining portion is still austenite. Okay, and after passing this eutectoid point, what happens? This austenite actually transformed into pearlite, and pearlite is what? That is the alternate layers of ferrite and cementite in a lamellar structure. This is what is the pearlite. So you can see this austenite portion actually converted into ferrite, and this red color one is cementite. So ferrite, cementite, ferrite, cementite, ferrite, cementite, this kind of lamellar structure. Oh, so this is what is the eutectoid reaction takes place in the austenite. So austenite converted into this pearlite. But what are these things? These things are the ferrite that already formed before coming to the eutectoid temperature. These are called pro-eutectoid phase. Okay, so in this case that phase is the alpha phase. So pro-eutectoid ferrite, this region is the pro-eutectoid ferrite. Okay, so in this microstructure just below the eutectoid temperature, you can see basically the ferrite is there. It is a two-phase region of ferrite and cementite. So ferrite is there and cementite is there, but ferrite, one kind of ferrite is present which is in the form of pro-eutectoid ferrite, this portion, and another ferrite is there within the pearlite as a lamellar structure. Okay, so ferrite is there in two ways. One is within the pearlite as a lamellar structure, and another one is before eutectoid temperature. Those has been formed. Those are called pro-eutectoid ferrite. Okay. So what is the first problem? The first part of the problem is you have to find out the fraction of total ferrite. Total ferrite means whether it is pro-eutectoid or eutectoid, what is the total ferrite? You just find out that, and the total cementite. So fraction of total ferrite and cementite, that you have to find out. So what you do? So this part is not very difficult. So you have to draw, since you have to find out the wet fraction of ferrite and wet fraction of cementite, Fe3C, wet fraction of cementite. These two things you have to find out, right? So for that, what we have to do, we have to draw the tie line and we have to use the lever rule, right? So if you draw the tie line very close to the eutectoid temperature, if you draw the tie line, okay, just below the eutectoid temperature, if you draw this tie line, then it has two phases. One is ferrite, another one is cementite. So first we have to know that what is the composition of that ferrite. So that you will get if you draw a vertical line here, okay, this composition. And what is the composition of cementite? That you will get on the other hand, which is 6.67, you know. Okay, and here it is. What is the composition here? You know, this point is 0.022%. Okay, this is 0.022% and this is 6.67% carbon. Okay, these are the composition that we know. And what is the overall composition where we are working? That was given that 0.35% carbon. That was given in the problem is 0.35% carbon, which is given. Okay, so you have identified there are two phases, ferrite and cementite. What is the composition of ferrite? The composition of ferrite is 0.022%. And what is the composition of the cementite? 6.67%. What is the overall composition? 0.35%. So what is the mass fraction of alpha present? So if you have to find out the mass fraction of alpha, you have to consider, say this is R and this portion is S. So to find out alpha, you have to take the other R. So S will be in the numerator, right? So S by R plus S. So what will be S? S will be this composition minus this composition. What is this composition where it will cut the cementite line? 6.67 minus this composition. What is this composition? It is 0.35%, right? Divided by the total length R plus S. That means this composition minus this composition. So 6.67 minus 0.022. So if you do this calculation, you will get that mass fraction of the ferrite. And how can you find out the mass fraction of the cementite? Simply 1 minus that. Okay, so if you do this calculation, you will get this is 6.7 minus 0.35 divided by 6.7 minus 0.022. So it is coming 0.95. So the ferrite that is present in the microstructure is 95%. That this 95% consists of both pro-eutectoid ferrite, that means this region, and eutectoid ferrite. So the total ferrite is 95%. And how much is cementite? It is only 5%. That is cementite in terms of wet fraction. Clear the first part? Now coming to the second part of the problem. Second part is that you have to find out the fraction of pro-eutectoid ferrite and pearlite. So pro-eutectoid ferrite and pearlite, that you have to find out. Okay, so you have to find out how much is the pro-eutectoid ferrite, that means this portion. this white colored portion, pro-eutectoid ferrite. And you have to find out the fraction of pearlite, this region. So you see, just observe just above the eutectoid temperature, say at point E, where this portion is the pro-eutectoid ferrite that has been formed, and the remaining portion is austenite. And after going through this eutectoid temperature, this austenite portion actually converted into pearlite. So basically, the amount of austenite present here, just above the eutectoid temperature, is same as the fraction of pearlite present here, and the ferrite present here is same as the eutectoid ferrite present here. Okay, so what we do, we have to draw a tie line just above the eutectoid temperature. Okay, so from that tie line we can find out what are the two phases present here in this region, alpha and austenite. So this is a combination of alpha and austenite. So what is the fraction of alpha? So that is corresponding to this fraction, that is 0.022. we know 0.022% carbon. And what is the composition of austenite present? That is eutectoid composition, that means 0.76. Okay, and overall composition you know, that is 0.35. Okay, so from here we can easily find out the pro-eutectoid ferrite. So what will be the pro-eutectoid ferrite? Pro-eutectoid ferrite. So pro-eutectoid ferrite fraction will be what? If you consider this is the point, say this is R and this is S. So to find out the pro-eutectoid ferrite, we have to take the opposite term, that means S by R plus S. Right? So what is S? Tell me. S is this fraction, this composition minus this composition. This is 0.76 and this is 0.35. So 0.76 minus 0.35 divided by, what is the total? R plus S. Total length is 0.76 minus 0.022. Okay, so this is what is the pro-eutectoid ferrite. So if this is the pro-eutectoid ferrite, then what is the amount of austenite? The amount of austenite will be 1 minus this, and that amount of austenite is exactly same as the amount of pearlite. Okay, so this is what is the amount of pearlite. So weight fraction of pearlite is same as the weight fraction of austenite. Okay, what will be that? That will be 1 minus this. So if you calculate this part, so you just take 1 minus this. Pro-eutectoid alpha. Okay, so in this way we can find out these two compositions. So here you can see their value. So for the pro-eutectoid alpha, it will come 0.56, and for the pearlite or the austenite, you will get 44%, just 1 minus this. Clear? Now what is the third part of the problem? The third part is you have to find out the fraction of eutectoid ferrite. That means only that fraction of ferrite which is there within the pearlite. Okay, so you have to find out the eutectoid ferrite. So only this portion which is there within the perlite you have to find out, because that is the eutectoid ferrite, because the other ferrite portion is the pro-eutectoid. So how can you find out that? It is as simple, because you know the total ferrite, because in the first problem you have done that. The total ferrite was how much? You have find out in the first part of the problem the total ferrite, that is 0.95, that you know. Okay, and you also know what is the fraction of pro-eutectoid ferrite. Okay, so you know total ferrite, you know pro-eutectoid ferrite, then what will be the eutectoid ferrite? Eutectoid ferrite will be, so eutectoid ferrite will be equal to total amount of ferrite minus pro-eutectoid ferrite. Pro-eutectoid ferrite. Clear? So that will be equal to 0.95 minus 0.56. Okay, so you can find out this fraction very easily. So this will be 0.39%. Clear? Now coming to the last problem in this tutorial, which is a bit conceptual problem. You see, the problem is, consider a hypothetical alloy consisting of two components A and B, where it is given that the percentage of B is 55, so obviously the percentage of A is 45. This is what is the overall composition basically. Okay, overall composition is known, and at some temperature it is found that it consists of a mass fraction of 0.5 for both alpha and beta phases. That means at some temperature it is having two phase mixture, alpha and beta phase present, and they are having the same weight fraction, 50-50%. Okay, and if the composition of the beta phase is 90%, 90% B, what is the composition of the alpha phase? This is what is the question. So let us first try to understand the question. So let us consider some two phase mixture is produced at that temperature, some temperature, and its overall composition is suppose known. The overall composition is what? 55%. So overall composition is known. It is known the temperature. That means you know this point. It is known that it is a mixture of two phases, alpha and beta. Okay, suppose this is the alpha and this is the beta phases. Remember, this alpha phase is a phase having A rich alloy. Okay, where the beta phase is basically maybe the B rich one. Okay, let us consider in the x-axis where we have shown the composition. This is represented as percentage, weight percentage of B, as weight percentage of B alloy, B component. Okay, that has been shown. Now it is known that the beta phase having composition 90%, beta phase having composition 90%. That means, so this is cutting at this point. So what is the composition of the beta phase? Corresponding to this one. Okay, so beta phase having composition 90%, that is known, that is given. So question is, what you have to find out? You have to find out what is the composition of the alpha phase present here. What is the composition of alpha phase? So alpha phase composition will be this one. So basically you have to find out this C alpha. This is what is the question. What extra information is given? Extra information is given. It is known that the mass fraction of this alpha and beta are 50-50. So 50.5 is the mass fraction of either W alpha or W beta. So this is known that W alpha or W beta, they are same, and that is 50%. So how to solve this problem? It's a very simple one. Let us consider this portion is R and this portion is S. try to find out what is W alpha, that means mass fraction of alpha. So already it is given that W alpha is 50%, that means 0.5, but we can write from the lever rule that this W alpha will be equal to what? W alpha will be equal to the opposite term you have to take in the numerator. So S divided by R plus S. What is this S? This S is composition of this point minus this point. So what is that? 90 minus 55. So S is 90 minus 55. Okay. And what is R plus S? That is the total composition from here to here. So 90 minus C alpha. 90 minus C alpha. Okay. So this value is known. Now W alpha is given 0.5. So from this equation you can easily find out the value of C alpha. So that is what is the question. Remember, the answer C alpha will be some value. If you multiply the some value and that percentage of B component. Remember, all the composition we have expressed as percentage of weight percentage of B component. Okay, so this is how you have to solve this problem. So W alpha is this. W alpha already known. You have to put W alpha as 0.5. So you can easily find out C alpha. Clear?